A sensor signal is the electrical output produced by a sensor in response to a physical input, such as temperature, light, pressure, or motion. The signals represents the measured quantity in a form that can be processed, transmitted, or stored by electronic systems. Just as the human nervous system sends signals to the brain to control movement and senses, sensors act as the nerves of a smart building, constantly gathering data and sending signals to a central control system. These signals enabled automated responses, ensuring comfort, security, and energy efficiency without human intervention. A sensor is like a translator between the physical world and machines, just as a human interpreter listens to one language and speaks another. A sensor detects a physical change or the input and converts it into an electrical message or the output that machines can understand. In this illustration, we see a temperature sensor mounted on the AHU's supply air duct. The sensing probe has a filter cap at its tip, covering the sensing element, an SMD or surface-mounted device. Although this SMD can measure both temperature and humidity, we will focus solely on the temperature signal to simplify our discussion. This SMD detects the temperature inside the duct, measured in degrees Celsius. The raw temperature signal is sent directly to the sensor circuit board, as shown in the image. The board then converts this temperature reading into an electrical signal, typically a 0 to 10 volts DC output, which serves as the sensor's final output signal. The input is what the sensor senses, or a physical quantity being measured. It can be temperature. Thermocouples and RTDs are examples of sensors that can detect temperature. Light detection. Photodiodes and LDRs, or light-dependent resistors, are commonly used sensors. Pressure. Strain gauges and piezoelectric sensors can measure pressure. Motion vibration detection. Accelerometers and gyroscopes are widely used for motion and vibration sensing. Humidity measurement. Capacitive or resistive sensors are typically used to detect humidity levels. All sensors require an input signal. They are useless if they cannot measure or interpret that signal. For sensors to be useful, they must accurately measure their input signal. In addition to the sensor's primary function, it is important to consider the type of output signal it generates, as this determines compatibility with data acquisition systems, controllers, and other interfacing electronics. The type of output signal from a sensor depends on its design and application. Here are some common types of sensor output signals. Analog signals play a fundamental role in conveying real-world physical quantities, such as temperature, pressure, light, or motion, into electrical form. Unlike digital signals, which represent data as discrete binary states, zeros and ones, analog signals are continuous, meaning they vary smoothly over time and can take on the infinite range of values within a given range. Sensors typically provide analog signals in two main forms: 0 to 10 voltage output, and 4 to 20 milliamp current output. The voltage output from sensors is typically DC or direct current, not AC or alternating current, because most sensors measure static or slowly varying physical quantities like temperature, pressure, or position, and generate a steady, non-oscillating signal. How temperature values correspond to a 0 to 10 volts DC sensor output. As previously discussed, when the sensor detects a changes, its internal circuitry converts this measurement into an electrical signal. So in temperature sensors with 0 to 10 volts DC output, the voltage signal is linearly proportional to the measured temperature. The relationship follows a predefined scale where 0 volts represent the minimum temperature, let's say 0 degrees Celsius, and 10 volts represent the maximum temperature, which corresponds to 100 degrees Celsius. Analog signals like 0 to 10 volts are widely used in sensors, but they come with two critical pitfalls. The noise sensitivity problem. Analog voltage signals are sensitive to electrical interference, especially in industrial environment filled with motors, relays, and power lines. Over long cable runs, this noise can distort the signal, leading to inaccurate readings. For example, a temperature sensor outputting, let's say, 5 volts corresponds to 50 degrees Celsius might appear as 5.2 volts or 52 degrees Celsius due to induced noise. Another is dead zero problem. The sensor detecting its minimum measurable value, or is there a complete system failure? That same 0 volts could also mean a broken wire, power loss, or sensor malfunction. Another common analog signal format used in industrial sensors is the 4 to 20 milliamp current loop. This robust signaling method offers several advantages. The 4 milliamp baseline serves as a live zero, allowing fault detection, while the 20 milliamp represent full scale. Just like in 0 to 10 volts, temperature sensors with a 4 to 20 milliamp output is linearly proportional to the measured temperature, which is 4 milliamp represents the minimum temperature and 20 milliamp represents the maximum temperature. Why 4 to 20 milliamp instead of 0 to 20 milliamp? If the signal range were 0 to 20 milliamp and the wire breaks or the sensor fails, the current drops to 0 milliamp. But 0 milliamp also means the sensor could be reading the minimum value. How would you know if it's working correctly or just broken? With 4 to 20 milliamp, if the current ever goes below 4 milliamp, the system immediately knows there's a problem, like a broken wire or dead sensor. Current signals are particularly valuable in industrial environments because they are highly resistant to electrical noise and can transmit over long distances, up to hundreds of meters, without significant signal degradation. This makes 4 to 20 milliamp the preferred choice for process control applications like temperature monitoring, pressure sensing, and flow measurement in factories and plants. Now let's talk about sensors' digital output signal. Unlike analog signals, which represent measurements as continuous voltages or currents. Digital signals convey information in discrete binary values, zeros and ones. This approach offers greater precision, noise immunity, and integration with modern computing systems. A pressure switch is a simple but critical device that converts air, fluid, or gas pressure into a discrete digital signal, typically an on-off, high-low, or open-close contact. As compressed air flows through the system, it reaches the pressure switch where the first stage, pressure detection, begins. The incoming air presses against a flexible diaphragm inside the switch, much like how a balloon deforms when squeezed. This diaphragm is the heart of the system, responding to every slight fluctuation in pressure. Next comes setpoint activation. The diaphragm's movement is resisted by a pre-calibrated spring which is set to trigger at a specific pressure, say 100 Pascal. As the air pressure rises, the diaphragm continues to press against the spring. The moment pressure surpasses the threshold, the diaphragm overcomes the spring resistance, marking a crucial transition point. With the set point reached, the final stage, switching, is set into motion. The diaphragm's movement activates a set of contacts. If the switch is normally open, the contacts close, sending a high signal to the control system. And if the switch is normally closed, the contacts open, producing a low signal. This simple yet effective process transforms continuous air pressure into a straightforward on-off signal, allowing the system to make instant decisions, whether to activate an alarm, shut down a pump, or trigger another safety mechanism.